Okay, I'm June Medford, and I'm from Colorado State University, a flyover state, if you would. But really, what I'm going to talk about is things that I care about and how the Genome Project could actually make a huge difference in the genome-write. And that is, in Colorado, we care about having environmentally sustainable systems. And we want to stop and be able to use the systems of plants in particular to design systems that are sustainable for life on Earth. Think of how we got to where we are today. Humans have long searched field and forest for food, fiber, and materials for shelters. There's no reason we should do that anymore. We can now design our future to be sustainable. There's no reason we are technologically able today to grow a house. Literally, let me repeat that, grow a house. We could do that today. In 10 minutes, I don't have time to talk about that. But what I want to do is talk about how we can design things to produce sustainable systems, what we have already done, and where is totally within our reach in the next few months. Okay, why plants? Plants have their own onboard energy generating systems. They self-assemble and they self-repair. Moreover, they've had a 4 billion year head start on environmentally friendly traits. So if we want to build environmentally friendly traits, we need to go back to plants. One of the systems we have already developed, we've already developed a computationally enabled sensors in plants, or what I call phytodetectors. We simply design proteins to bind the substance of interest in computers. This is with David Baker at the University of Washington, designs our proteins. We then encode them in our DNA, and then I enable them in plants. These are our first generation plants. You can see our little plants. I put about 10 nanomolar of the explosive TNT in the agar. Our plants detect that and report that in the chute. And you can see here the plants are indeed responding to this in both from the soil, in the chute, and they can also detect it in the air. Importantly, the amount that we are detecting is really quite good. Since we have a computationally designed sensor, the parts that we're detecting is about 23 parts per trillion. In case you haven't done the math, that's 1 drop in an Olympic-sized swimming pool, 1 meter deep, or that's about 10 to 100-fold better than what a dog can detect. These are systems we already have today. With Genome-write, we can go and make this even better. So we'd have a computationally designed system in the lab for a lab chemical called DIG. And we want to be able to detect a very, very brief exposure, because when Jeff tries to sneak his bomb on the plane, he's not going to stop and put his bomb down next to my plants, right? My plants have that amount of time to find the bomb that Jeff has. 1 exposure to a laboratory chemical, they detect and remember it for 3 days. Not bad. So we can already do that today. We can make sustainable systems. Instead of taking off your shoes, pull out your laptop, take off your belt. This is my vision of a future airport entrance, okay? So or the entrance to a sports arena or Broadway theaters, just go by a nice little garden center. We won't be able to find an individual, but maybe if you're in a group of the 10 bad guys, we'll come and look at your luggage. Okay, so we can do that today. That is literally doable today. And again, but I want to come back to where can we go with projects like Genome-write. Nature, again, has had a 4 billion year head start. Let's go back and learn from nature and adapt traits for human and environmental use. For example, one thing everyone in this lab or in this room or in watching at home or wherever needs is water. Everyone needs water. Here in New York, there's elaborate systems to purify the water so we can flush the toilets, drink the coffee, and do whatever we need. And it takes a huge amount of money to make water and make it pure. Plants naturally filter and secrete or seep water. This is a photograph of some plants growing in my lab. And if you can see over here on your right, you can kind of see here. Let's jump up here real fast. This is not dew. These are plants that took up water and are secreting it out of their leaves. This is actually a natural process. I did not invent it. And if you take a look at that water, they secrete. This is a bottle of Fuji water that was in a hotel room when I was in Chicago recently. The water that plants secrete is really pure. Matter of fact, it has properties similar to that of the bottled water that you can buy. And so what we want to do then is we want to be able to use these traits and engineer plants to purify and filter water. Imagine that, to filter out gray water and filter out contaminants. Moreover, one of the greatest limits to the life on Earth is water. And imagine the way we deal with this now in the West, we desalinate water, we desalination plants, and this was an article in Science about the drought you can't see from the aquifers we're pumping dry. Water is limiting to life on Earth. However, water is abundant on Earth. Most of it's just a tad bit salty. So imagine if we could, with projects such as Genome-write, develop positively ways to filter. If we could do this, to filter seawater, we could provide unlimited water for life and sustainable life on planet Earth. Thanks. I'll be glad to answer any questions. Yes, indeed. So there's a variety of plants. If you want to be able to pump huge amounts of water and filter them and provide it for life on Earth, you're going to need to do that in very large plants, not the little Arabidopsis plants we use in the lab. I would use a tree. Yeah. Okay. Yeah, Jeff.
What are the prospects for engineering tree genomes?
What are the prospects for engineering tree genomes? Clearly, we need Genome-write to be able to take and put these circuits in a tree. They're really, obviously, much larger genomes with trees than they are with Arabidopsis. We need it, folks.